Good afternoon, everyone. Today is the second day of. Am I audible to everyone, sir? Himanshu, sir, am I audible
Hi.
to you?
Yeah, yeah,
Okay,
audible. So your voice is little bit means volume is less.
okay. Now, sir, is it okay? The
Yeah,
volume?
yeah, little bit okay.
Okay, sir. Good afternoon, everyone. Today we are in the next second day of our 6 days online ATAL faculty development program on next wave advancements in next generation communication. Today with me, uh, Dr. Himanshu Bison Mishra for the session 3 speaker. Uh, he received BTech degree from ECE from Biju Patnaik University of Technology, Odisha in the year 2009. He got his MTech degree in Communication and Signal Processing from ECE department from NIT Rourkela. Also, uh, also Rourkela, India in 2012, and the PhD degree in Communication and Signal Processing from Electrical Engineering Department of IIT Kanpur in 2016. In 2017, he joined as an assistant professor of Electronics Engineering Department of IIT ISM Dhanbad. Currently, he is working as an associate professor with electronics in the Electronics Engineering Department of IIT ISM Dhanbad. His current research interests include the area of parameter estimation, detection, optimization for next generation of wireless communication technologies such as OTFS, IRS, OFDM, IRS, OTFS, terahertz communication, ISAC, multi-antenna technology, etc. He is also focusing towards the real-time implementation of the proposed algorithms on software-defined radio boards. He received the Best MTech Award in the Communication and Signal Processing domain from NIT Rourkela in the year 2012. He is currently leading 3 DST-funded projects and 1 DOT-funded project in the domain of 5G and 6G wireless communication. Till now, he has published more than 30 research papers in reputed journals and conferences such as IEEE Transaction on Wireless Communication, IEEE Transactions on Signal Processing, IEEE Transaction on IEEE Transaction on Communications, IEEE Communication Letters, IEEE Wireless Communication Letters, IIC, Globecom, etc. Furthermore, two of his research articles on OTFS waveform scheme has been listed as the best reading article in IEEE Communication Society. Today, Sir will discuss about the fundamentals of physical layer technology for 5G and 6G communications. So now I am uh, it is our honor to have Sir as a speaker in this session. So I'm giving you all the um, Sir. Please, you start your session.
Okay. Thank you, Pradeep. Thank you for this introduction. So my screen is visible or not? Please.
Yes, sir. It is visible.
Okay. So as per the today discussion, I would like to provide a fundamentals of basic physical layer technologies. Okay, so what physical layer technologies has been used from 3G to 6G. So few technology I will cover, and I will also cover what how it is being evolving one by one. So before that, let us me give you some brief outline of this. So initially I will like discuss about what is the evolution from 1G to 5G. If you can just see history of mobile communication, you have 1G first generation. It is based on what? Based on the analog transmission, right? So it is based on analog, and then So here analog, so 1G has three different technologies. One is advanced mobile phone system, one is total access communication system, NMT. This was there earlier. Then digital communication has been introduced in 2G. Okay, so you have like SMS system came and all these system came, CDMA, GSM, so DAMs, all these things came in 2G. Then 3G 3G introduces little bit fast wireless internet access that came in 3G, like HSPA, CDMA 2000, all these things. Then you have 4G. 4G just to add, or currently also 4G is there, and so 4G or LT, what you are telling, long term evolution. It has a little bit advantage than CG that here OFDM has been introduced. So we'll discuss what is OFDM is, and MIMO technologies has been introduced, and diversity has been introduced. The diversity, MIMO, that means antenna diversity, OFDM, all these things are the key physical layer technologies for this 4G. So we'll discuss about these things. So these are the some spectrum of 1G, 2G around like 800 to 900 megahertz in 1G. Similarly, you have spectrum has been slowly increasing till now. In like in 5G, I will discuss later next. So what is 5G? You have 5G. We have like three different technologies, three different use cases. We have one is enhanced EMBB. It will focus high data rate. That is enhanced mobile broadband. So it focus on high data rate, high traffic volumes. Another one use case is massive machine type communications. It focuses on the massive number of devices, how it can be connected with a low energy consumption. Another kind of use case is URLLC, that is ultra reliable low latency communication. Here focus has to be communication has to be low latency simultaneously, along with it should achieve a high reliable communication. For example, vehicular communication or moving. So vehicle, there may be a vehicle, if some information vehicle has to get immediately, that should be low latency should be there, and in addition to that reliability should be very high. Otherwise wrong information will get by the vehicle, there may be, it may cause to accident and all these things. That is the very one strong use case of URLLC. So EMMB, all these things are separate. It has separate needs. It has separate physical layer structures, separate kind of what you can tell, the data rate requirement, reliability requirement, all these things. So again, this you can see that these are basic spectrums in 5G. FR1, as you know, that it is 450 megahertz to 6 gigahertz. That is frequency. Two different frequency ranges are used. One is FR1, one is FR2. FR2 has 24.25 to 52.6 gigahertz, and FR1 supports both FDD and TDD. It supports only TDD. There is some reason, like because high frequency, there is some observation happened. That's why FDD it is not being considered here in FR2. Bandwidth, you can see maximum bandwidth 400 megahertz, and then maximum number of sub channel is OFDM that is being used in 5G. That is 3300 sub channels. FFT size is 4096. So these are some control channels. Maximum number of control channels are 16. These are some like uplink, what you have to use, downlink, what physical layer technology you have to use. Multiple access being used is WebDMA in 5G. Okay, so let us come to the our discussion. Key physical layer technologies for 5G and 6G. We'll discuss about MIMO, massive MIMO, OFDM, and OTFS. And there are also many 5G technology that we are not discussing here, that is millimeter wave communication. And another 6G technologies, these three are 6G. It will come not only 6G, you can tell 6G or 7G like that. So 6G mostly focusing currently on integrated sensing and communication and RIS. These two are the key current under development things. And OTFS is something that is an interesting modulation technique. So let us come to the background on the discrete time wireless system model. We know that design of there is some noise is there.
mute your audio. Please mute your audio.
मिट लागल प्रॉब्लम दृष्टि
Please mute your audio.
देखने ले मारा वाला कौन कर दे ठीक है भाई जा सुबह से फोन करना मैडम के लिए एक उनका था इससे हमारा देखो देखो डिस्प्ले होगा क्लास করতে ভাই বলি কোন একটা ক্লাস করছি বুঝলেন না ওই তো না ये बाबन नाम और অনেক ভালো লাগলো দাদা লাগে 1 4 PhD but please right you join over you got it
Please mute your audio. Please mute your audio.
Okay, so one point whenever we are designing any
Please.
আমরা নেই রেবো খান না দিচ্ছে দিচ্ছে সর খাকে দাম দিয়েগা
Has not muted his audio. Please mute.
শেয়ার করো
okay, so if we can discuss, so here just 1 second, am I audible, Pradipta?
Yes sir, you are audible.
Okay, so design of wireless communication system. Whenever we are designing any wireless system, so we have to focus basically two primary things. One is what? Throughput. Another one is reliability. What is throughput? Throughput is the bandwidth into spectral efficiency. So if you spectral efficiency, you know that spectral efficiency means bits per second per hertz. How many bits can be transmitted from one end to another end without having any error per second and per hertz. That will give the spectral efficiency. So if you multiply with bandwidth, then you can have the throughput. Then another one is reliability. Reliability means what? Bit error rate. How much bits you are getting, that it has to be less in error. That means you will get better corrected. That means you have transmitted some bits, it has to be correctly received. How much correction is there? So that will means you can tell that less bit error rate. That means the reliability is high. So these are the two key points that will be, that we have to be any wireless as a wireless engineer. So you have to be focused while designing a system. We have to be these key points you have to be keep in mind. That means it should have high throughput, it should have highly reliable. Okay, so that's why, so in order to design in this wireless system, we have to be focused. One is fading channel. So what is the fading channel? You know that two different type of fading channel. We have the large scale fading, small scale fading. Basically, small scale fading has a key on that it has a very, that means it comes due to the multiple paths. That means whenever same signal is transmitted, it is getting reflected by various reflectors. So that will get added at the receiver. That will provide a significant degradation of attenuation in the signal received signal strength. That will happen for a small duration. That is known as a fading. Okay, so there is fading came due to two different type of parameters from the channel. One is multipath nature, another one is time varying nature. Due to multipath nature of the channel, we can have flat fading and frequency selective fading. Due to time varying nature of the channel, you have slow fading and fast fading. So there are also various parameters how I can judge what kind of fading it is facing. That is like delay spread. One is its inverse is coherence bandwidth. Another one is delay uh, uh, Doppler spread. Its inverse is coherence time. So based on the relationship with signal bandwidth and all these things and signal duration, all these things, you can have different kind of fading. So this will basically lead to one you take from this two, another one you take from this two. That means you can have four different kind of channel scenarios. What are those? Frequency selective fast fading, frequency selective slow fading, then frequency flat fading and fast fading, then flat and slow fading. So all these four channels, when you know that all these four scenarios, how we can design a wireless system for this. So while designing a system, we have to first we have to frame a system model equation. What is the system model equation? The relationship between transmit signal and the receive signal. You can see the equation 1, it follows for a single carrier system. If you want to transmit x of n, you want to receive y of n, so it has to be follows this equation. You can see G corresponds to the channel. GL corresponds to the Lth complex channel tab. Why you have summation? Because you have multiple channel tab. That is coming, that gives rise to frequency selective nature. Then fast fading, because since you are fast fading, that's why it should be function of time. That means that each time the channel tab or channel LF tab at time N1 is different than at time N2. So this is the basic system model that we can follow, mathematical system model that we should follow for frequency selective fast fading. Similarly, frequency selective and slow fading. That is for real time example, if you are sitting inside a room, that the complete scenario is frequency selective and slow fading. For this case, you can have this scenario. That means here you can observe there is GL is not function of N. Why? Because it is slow fading. The channel is constant through multiple time. That's why you can have this equation. That is simply, you have seen, this is just nothing but the linear convolution. So you can tell that channel is a LTI system. For frequency selective and slow fading channel is nothing but an LTI system. Okay, that's why you have a simple linear convolution with the channel tabs with the transmitted symbol. If you can go for next, that is flat and fast fading, you can have just, since it is flat fading, you have a single tab, only G. Okay, you have one tab that is being function of time because you are considering a fast fading channel. Okay, then you have a simply G of n multiplied with the signal at nth time and plus adding some noise. So this is our receive signal. So, but next you can go for flat and slow fading. What will happen? The difference is you have a simple Z which is not a function of time because you are considered slow fading. Now you can see that four different system model equation based on four different channel scenarios. So that you can consider while doing any research, developing any channel estimation algorithm, detection algorithm, all these things. Next point. So let us see the inter-symbol interference. What is inter-symbol interference? It came in frequency selective channel. See, mostly practically we will get fast two set channels. One is frequency selective fast fading. This will come when you are moving in a bike or vehicle. So that means you are getting frequency selective and fast. Second one, this is coming inside to the room. You are sitting and all or is walking. Like these two are very common. Frequency selective fast fading and frequency selective slow fading. These two are very common. We'll focus first frequency selective slow fading channel. If you focus frequency selective slow fading channel, what you can observe that equation 5 you will observe. What you will observe here, if you want to find, if you consider receive signal at mth time, it should have relationship only with the transmitted signal at mth time. Okay, but what happens due to the multipath nature of the channel, the received signal at mth time is actual signal, the transmitted signal, it is a function of actual signal plus some interference from the previous symbols. This part is known as inter-symbol interference. You getting? So that means inter-symbol interference is coming due to the multipath nature of the channel. That is a negative point of frequency selective channel. So now the question will come, how we can mitigate, how we can nullify the inter-symbol interference. Then the developers, then the system designers, scientists are working on this. So engineers have developed a powerful modulation or waveform technique that is known as OFDM, which is completely nullifying this inter-symbol interference for frequency selective slow fading channel, that is known as OFDM. How it works? So that means, so how it works, that we'll discuss later. Before that, what we'll discuss, why fading channel, what is the negative effect of fading channel. Okay, so that means if you know that if you don't have fading channel, suppose wired channel, we have not wireless channel, so it will mostly look like this: y equal to x plus noise. X is transmit signal plus noise. So if, let us calculate the probability of error for this channel. If you calculate the probability of error, you see that, and let us take energy or power of x is ex, and the power of w, let us take, that is n naught. So what is the SNR? SNR is ex by n naught. So if you compute the probability of error by considering BPS system, so you will get the probability of error for AWGN channel is Q function of square root of SNR. What will the probability of error for Rayleigh fading or fading channel? Simply frequency flat and slow fading channel. This I have considered. For here, what is the probability of error? This is the derivation. If you derive the probability of error, you see that probability of error will be nothing but 1 by 2 whole into 1 minus SNR, because I want to compare with AWGN. So whatever SNR definition here, same SNR definition. That means this is a function of SNR, this is function of SNR. Here you can check that this is approximately equal to 1 by 2 SNR for high SNR. So you can check that probability of error for AWGN is Q function of square root of SNR, whereas for fading it is 1 by 2 SNR. Now you can see how much significant degradation we are getting for fading channel. You can check here. Here you have this red line is a probability of error with respect to SNR plot for AWGN, whereas this one is the SNR plot for probability of error plot for the fading channel. Now you can see that at 10 dB, you are getting 10 to the power minus 3 beta rate, which is very less, whereas you are getting here around 10 to the power minus 1 beta rate for fading channel. Now you can see that how much degradation it happened in fading wireless channel. Now, what is the reason of this degradation? So the reason is, what the reason is, if you can see that, if you can see the system model here, what is the power of Hx? It is h mod square into energy of x, right? Energy of Hx, or you can tell power of Hx. Power of Hx is h mod square into power of x, but the power of noise is n naught. So when you cannot recover the system, if this power is significantly less than this power, if signal power, actually this one is signal power, signal power is much more greater than the noise power, so you can easily recover the signal. That it means probability of error is less. Now if signal power is less than the noise power, so what will very difficult for us to recover this thing, that is known as very high probability of error. This scenario is known as deep fade scenario. That means you can tell that channel undergoes deep fade. For that instant at which h mod square into energy of the transmit signal is less than the noise power, that means are you getting, that means the noise variance, noise power, the channel mod square, this is a critically affecting the signal recovery. You want to correctly recover the signal or you cannot, that depends on the channel parameter. So that means that will give the deep fade. Okay, so that, so what is the probability of this deep set? You can find this probability, that probability you will see that it is 1 by SNR, which is nothing but approximately same as the bit error rate. That means this due, if you have a high probability of deep fade, you have high probability of error. That means you cannot recover the original signal. So that is the reason why we have to mitigate this deep fade. We have to do something, that we have to remove this deep fade. How we can do these things? That's where diversity come into the picture. Okay, so you can now see how system has been evolving. First thing I told you, only fading channel, y is equal to hx plus n. So what we observe that we are not getting that much of significant bit error rate improvement here. So that's why diversity come into picture. Diversity means particularly there are three kind of diversity: time diversity, frequency diversity, and antenna diversity. We'll discuss here antenna diversity. What is antenna diversity? You will transmit same symbol through multiple antennas, or you receive same symbol through multiple antennas. Based on that, you have three different kind of antenna diversity. One is what? Single input, multiple output. It means what? You will transmit same symbol through, you will transmit one symbol through one antenna. However, you will receive same symbol through multiple antennas. That means the transmitter contains only one antenna, receiver contains multiple antennas. That is CMOS system. Similarly, MISO system, transmitter contains multiple antennas, receiver contains single antenna. Last one is MIMO system. That is transmit contain many antennas, receiver contain also many antennas. So this type of three kind of, so now in pen and paper you wrote that is fine, or now the question will come that how you can transmit the signal, how you can receive the signal. individual diversity type it is known as receiver diversity CMO, MISO or MIMO. If individual technique requires different designing techniques, that means different signal detection schemes are required, different channel estimation techniques are required. So let us discuss one out of that, one and two. One is what we are discussing, what is receiver divergence, that is single single transmitting antenna and multiple receiving antenna. Here you can see that if you have only one transmit antenna and mainly receiving antenna. So what is the system model? I always tell you that first point you have to write a system model. Let us consider NR number of receiving antennas. So each channel, let us assume that each channel follows complex Gaussian. This has to be complex Gaussian. The C is missing. So complex Gaussian with zero mean and variance 1. This is circularly symmetric Gaussian random variable. So if you can see the receive signal will be nothing a vector because you will receive NR number of receive samples. That is Y vector. So that you can write Y vector equal to H vector. What is H vector? H vector contains all the different channels from one transmitter to all NR number of different receive signal. That is NR cross 1 channel vector. So this is the system model that will receive, that means this Y contains all the receive signals from NR number of antennas. Similarly, this size is all are NR cross 1 vector. So now the question will come how to detect this X. Okay, so then there is a powerful technique known as maximum ratio combiner that is being used for the detection. What is maximum ratio combiner? What you have to use? Some vector we have to multiply with the receive signal that will combine. Combiner means what? It will combine the receive samples. So through some weights, what are those weights? Those weights are nothing but elements inside this vector. This is a vector H by H norm. So that means what? The channel, knowledge of the channel you know, then you form a vector. What is that vector? H by H norm. Then you take this Hermitian, then multiply with Y. Okay, then you obtain, then whatever signal you obtain, that that is a soft information that you put in the demodulator, then you'll get the actually transmitted constellation signal. Are you getting that? You know, I think so. That is not how you can do the MRC. So after, so MRC will provide you what? So let us see how this MRC is improving the bit error rate. Now you can observe that what is the probability of deep fade in CISO system that we have done previously. What is the probability of deep fade? Approximately 1 by SNR. Now, what is the probability of deep fade after applying MRC? That you can see that is 1 by SNR to the power NR. What is NR? NR is the number of receive antennas. If you increase receive antennas, 1 by SNR is generally SNR is higher than 1, right? SNR signal power is high. So this component is generally less than 1, this parameter 1 by SNR. So obviously you will get NR increasing, so this will be very small. So that means what? Probability of deep fade is degrading. Okay, more details if you see that H norm square, analyze the H norm square. H norm square follows a chi-square distribution. Then more details you can go from the book and papers. Okay, so I'm just telling you the fundamental behind this is it is reducing the probability of deep fade significantly. Okay, so then another technique is transmitter diversity. How to transmit symbols using the multiple antennas at the transmitter and one antenna at the receiver. Then what you have to do is, so here the concern is you cannot follow MRC technique here. Here you have a different technique you have to follow that is known as maximum ratio transmission, MRT. So that is what you have used a vector that is known as precoder, which is nothing but same thing. H1, each of the element is, so that means here your system model is quite different than previous one. As I told you, each diversity technique have different system model. Here you receive signal only one sample because you have one receive antenna and you have many transmitting antenna. Each transmitting antenna to the receive signal you have one channel parameter. So you have, that means NT number of channel parameters here, H1, H2 up to NT. So that you have a Y vector which is H transpose X plus noise. So that will provide. So now the question is how I can design the transmitter and receiver such that I can receive the X correctly. So for that, what you have to do, we have to transmitter, we have to do, instead of transmitting separate all the elements of X to be different, what you do, will transmit a pre-coded data. What is the pre-coder vector? This one is the pre-coder vector. H1 by H norm, H2 by H norm, HNT by H norm, this one. So what is the precoder you have? V into X. Okay, so this you have to multiply with some symbol X that you transmit. This is our X. So X is, that means you have a vector which is a depend on the channel, multiply with some symbol X that you transmit, and receiver side you will get this one. Y equal to H norm X plus W. So that will give you same probability of error as you have done previously. Okay, that will also give you the dive. That is the probability of error is 1 by SNR. Probability of deep fade will be 1 by SNR to the power NT. Like previously you got NR to the power NR because NR number of receiving antennas. Here I consider NT number of transmitting antennas. So I will get 1 by SNR to the power NT. So that means there you are using MRC. Here you are using maximum ratio transmitter. Another here one key point, you can see that the transmitter, the precoder depends on the channel. That means transmitter side, I should know the channel. That is very difficult. That means it requires the feedback from the receiver to the transmitter. So that's why there is another technique that is known as orthogonal orthogonal it is known as orthogonal space-time block coding, OSTBC. Okay, this technique, if you use this technique, that is OSTBC technique, if you use, or you can tell for two antenna, two transmitting antenna, that is Alamoti coding technique. Without knowledge of the channel at the transmitter, we can achieve the same probability of error. That means the key point is how you will get better probability of error if you have more diversity order. What is the diversity order? Here. NR. NR is the diversity order here. Here diversity order will be NT. Okay. So more and more diversity order, you have a better probability of error. Let us come to the MIMO system. So what MIMO system, how you can do these things? MIMO system is what? You have multiple antennas at the transmitter and multiple antennas at the receiver. So that have the different system. But now you can see that this H is now a matrix. Y is a vector. This is a very well known equation as a linear equation. So you have all of us, we know that from the linear algebra concept. So what is the problem here? We know H, we know Y, how I can get X? That is the detection problem. So that means we can solve some linear equation format. So that's why. So here, so based on, so there are various type of detectors you can follow. One is maximum likelihood detector, which is a non-linear one. MRC, I told this is a linear detector. Zero forcing and MMSC. These two are some detections we can use. These are the linear detector that you can use for the MIMO cases. Okay. Here we can also apply OSTBC in MIMO. If we apply OSTBC, orthogonal space-time block coding in MIMO, your diversity order will be NR into NT. That means what? Suppose for an example, you are using two transmitting antennas, four receiving antenna. Your diversity order will be 2 into 4. So 8. So 8 diversity order you will get. That will significantly reduce your bit error rate. Okay, but that you cannot get by zero forcing or MMSC. That you can get if you use OSTBC along with MRC. And you have to combine this OSTBC with MRC. See, MRC you cannot apply straightforward. There is a key difference between MRC, ZF and MMSC. Okay, MRC will give better for at means if you have less noise, so you will get better. Zero forcing you will get better at low means at high SNR. Zero forcing will reduce the inter-symbol interference. That's the inter-frame interference in MIMO. That will reduced by the zero forcing. That will nullify by zero forcing and MMSC. Whereas MRC cannot reduce that. But zero forcing will have negative effect at low SNR. Okay, so that's why it will not perform better. That's why MMS is a better choice. Low SNR and high SNR everywhere. So you can have MMS is a better choice. So okay. So fine. These are some fundamental things I told about the various detections. And obviously optimal is the maximum likelihood. But the negative point is what? Maximum likelihood highly complex. Okay, its computational complexity is very high. And it is very difficult to implement on the hardware board. Okay, so that's why. Okay, next come to another point that is known as multi-user MIMO system. What is multi-user MIMO system? That means instead of transmitting to only one user, one base station will transmit to multiple users. That you will be getting lot of advantage over the MIMO system. What MIMO system is doing, one transmitter, one user has only antennas, receiver has many antennas. So instead of that, what we can do is one transmitter, if you take many antennas, whereas many single antenna users you can keep, so that will give better. That means spatial multiplexing gain will get better if you use multi-user MIMO system. But multi-user MIMO system has some negative points like interference from the multi-user, then acquisition of channel state information. That means channel estimation will be a little bit difficult task for multi-user MIMO system. And user scheduling, what is the user scheduling? To which user you will communicate now, what will be done later, that is known as user scheduling. That is a different task, difficult task in multi-user MIMO. That's why in 5G it came like that is known as multi-user massive MIMO. What is the massive MIMO? So what is the, this you can look here. You have antenna, you have a thousands number of antenna at the base station, more than 100,000 like antennas. So what it will happen that if you that kind of antennas here, the user has only single antenna, it will get a very high spectral efficiency in comparison to only multi-user MIMO. That's why spectral, what is the massive MIMO has the advantage that spectral efficiency is very high. Then it has energy efficiency. What do you mean by energy efficiency? How much data rate you will achieve use in multi-user. Suppose some data rate you are achieving by consuming some power. Here what will happen, here you will achieve in that much of power, you will achieve better data rate. That's why it is known as energy efficiency. And simple signal processing technique will follow. That means linear signal processing technique will follow during uplink and downlink. What is uplink? Uplink is when user is communicating to the base station, when downlink is base station is communicating to the user. So two different kind of processings will happen. You can see here downlink and uplink. This diagram, through diagram I have shown here. So now let us see any uplink system model. See that uplink is what is happening. Uplink system model means users, multiple users are transmitting data to the receiver. What receiver will do? Base station has to detect which user transmitted what. Suppose two users are there. Two users has been transmitted to the massive multiple base station. Sorry, one base station. It has massive many antennas. So that means it has to be detect this data is from user one. This data is from user two. So how the detection happens? So that is a very simple. The detection can be done by linear through linear processing. That will happening how? Like this. This is happening due to a very interesting concept that is known as law of large number. Yeah, this one. What is this law of large number? If you see that P Hermitian P, linear combining of two random variables, that will gives like simply sigma P square. If P and P both are obviously both are same vectors, if you take different vectors, they will get simply zero. That means if you two different independent random variables you have, it's orthogonal to each other, and same random variable will be correlating and you are getting a single only sigma P square, that is the power. You are getting only single. Okay. Similarly, central limit theorem, if you have this thing, it will be this one is tending to zero. However, 1 by square root of n is tending to some Gaussian. That is normal distribution. Having zero mean and variance is this thing. This will happen at n tends to infinite. See, n makes the vector length to be larger. Okay. So n correspond to this n tends to infinite has a relation here, massive MIMO system, with the number of antennas. Due to the number of antennas, what happening that this G vector, this is the channel matrix Z, so it is M cross K. I think M is the number of antennas. That M is too much of high. If that is too much of high, what is happening? That you can use a simple processing here. Yeah, here you can understand. G Hermitian into G will be nothing but simply a diagonal matrix D. That is a very interesting equation 9. If you understand equation 9, your job will be done. That will happening G Hermitian G. This type of equation 9 you will not get if you use less number of antennas. Okay, that's the beauty of massive MIMO. Okay, so that leads to some interesting expressions. I will just tell you now. If we'll use in uplink we are discussing, that means what? We have to use a linear detector at the base station. That linear detector is what? Simply G matrix we can use. If we use that, simply G matrix here, yeah, here. MRC, so three different kind of linear detectors you can have. If you use MRC, your detector will be simply G matrix. Zero forcing, it will be G into G Hermitian G inverse. MMSC, it will be this thing. Only MRC, if you just take only MRC, you see that how interestingly you don't have any multi-user interference. You will not get any multi-user interference here. These terms will be completely zero. Finally, you will get this thing, this expression. This expression is what? So that means you can get that all this interference from the multi-user, that will getting reduced to be zero, and finally so you can have this kind of expression. 14 and 15 you can check. So if you can summarize, if you can look here, 14 and 15 expression, what happens? M tends to infinite, you don't have any interference from the other user. Okay, but the rate is log base to 1 plus beta k uk. What is this meaning? Kth user. For kth user, that means the received signal correspond to kth user. Only it has the data from the kth user. It don't have any data from other users. So here, if you consider the power of the user, if you divide, so see how that is a beauty of massive memory. That means you are not getting any user interference here. Another one point is what is the energy efficiency. But the mean by energy efficiency, what you do, you divide energy of user by AEU divided by M. What is M? Is number of antennas. So if you divide energy of user by number of antenna, so what will happen? That what you see, that you will get this thing. EU, that means RKMC. So that means here, okay, yeah, something okay, fine. So what is, just 1 minute, so if you just PU, yeah, so PU is what? The power of user. What is happening? You write PU equal to EU by M. Okay, then you will obtain that this expression. That means you made the each user power to be some divide something divided by M. That means what? Your power has been reduced. So you have used reduced power of user, but still you are getting a very good data rate. That is the thing, is that is the known as your achievable rate is better by using less power. So that is known as energy efficiency. Okay, so let us come to the next thing, that is OFDM. What is OFDM? As you have just remembered from the previous slide, this I told you that if any if you'll focus frequency selective slow fading channel, what will happen at mth receive signal, it has the actual data is mth transmit signal. However, these are the data that the signal came from the previous samples. These are known as the inter symbol interference. It can be nullified using OFDM. How it can be nullified? So very basic things, what you have to do, you have to transmit the symbols through different in the frequency domain. How it can be done? You have the symbols, right? You have the symbols here, bits. From bits you will get this constellation symbols, then make serial to parallel, then do IFFT. What will happen to the IFFT? That means that symbols you are transmitting in frequency domain, so you have to convert into time domain. Then you add a cyclic prefix. The cyclic prefix will ensure that there will not be any interference from the previous OFDM block. And it has a beauty, another beautiful advantages that I'll let you know. So that transmit, this is the transmit signal that will be in time domain. So what will happen? Receive signal, you have to remove CP, then you have to do serial to parallel conversion, then FFT, then parallel to cell conversion, then you can use the demodulator. So all these things will the basic concept of OFDM. Now if you just understand what is basically happening, you just consider that what is the inside of the OFDM is happening. You transmit the symbols. Let us consider m number of subcarriers, S0 to Sm minus 1. This many subcarriers, m number of subcarriers you have transmitted. Okay, from the constellation. Then what will happen? First thing what you have to do, you have to do IFFT operation. So what is the IFFT operation? That you can write mathematically. F Hermitian S. What is F? F is nothing but a normalized DFT matrix. Understood? So F is a normalized DFT matrix. So this you can expression is like this. F X equal to F Hermitian S. Now what you do, as I told you, use some L tab channel. This is a channel, complex channel tab. Then as I told you that what the receive signal you will receive after removal of cyclic prefix. Once you remove the cyclic prefix, you will receive the time domain. What you receive? This one. That is the very interesting thing. If you don't use cyclic prefix, your receive transmission expression will not be like this. The relationship between receive vector and transmit vector is like this. See, R equal to some circulant matrix multiplied with X. What is X? This one, the time domain. Okay, plus noise. That means receive signal will be a circulant matrix into this thing. The circulant matrix is this one. This is the circulant matrix of a channel. What is circulant? That means you have L tabs. How you will form the circulant? G0, G1, GL minus 1, all are zeros remaining. So you have a M cross M circulant. M is the number of subcarriers. Okay. This circulant matrix only get formed if you have transmitted along with the cyclic peaks. If you don't use cyclic peaks, if you pad zero padding, so someone may ask that instead of cyclic peaks, can I have zero padding? Yes, you can have zero padding, but you will not get this expression. What is the advantage of this expression? The circulant matrix can be easily, not easily, the statement is wrong. The circulant matrix, if you find eigenvalue decomposition of circulant matrix, what you will, what you can express its eigen matrix is nothing but the IFFT matrix and FFT matrix, and the eigen values, these are the diagonal elements. The eigen values are nothing but frequency domain response of the channel. That means it is diagonal element. It contains capital G naught to Gm minus. What is capital G naught? Capital G naught is the, if you have the small G0 to GL minus 1, that is the time domain channel, you take its FFT, you will get the G naught to Gm minus. That means its corresponding frequency domain representation. So discrete frequency representation is G naught to Gm minus 1. All the frequency spectrums are M number of subcarriers that will be there in the diagonal element. So you have a circular matrix can be decomposed like this. Okay. Then what you do? So you completely write this expression here. Here. So what you have? So you have right side F. So F into X. Okay. F into X. So X is equal to F Hermitian S. So F Hermitian will be identity because F is a normalized matrix, normalized DFT matrix. So final right side you will get S. Okay. S you will get right side. If we'll put this thing. So S. What will happen then? Gamma is there. Okay. This S into what? F Hermitian. Okay. So F Hermitian. What F Hermitian is here? So what you will do here? So that means R is nothing but simply F Hermitian gamma into S. Now the question is how I can remove the F Hermitian? Just multiply F. That's why F is multiplied here. F into R. That's why you have to do FFT at the receiver. Okay. If you do F into R, what you have? You have a diagonal matrix into S plus noise. So you can now observe all the receive vectors. It is N cross 1. M cross 1. All the receive signals in the M number of subcarriers will be nothing but simply multiplication of the individual diagonal elements with the transmitted. That means simply you will get this expression. That means receive signal at kth tone equals to channel response at kth tone multiplied with the transmit signal at kth tone plus noise. There is no intersymbol interference right now. Now you look this equation and you look this equation. Equation 16, that equation. What is happening here? Here you have an intersymbol interference. Here there is no intersymbol interference. What you modified, you did, you transmitted in the frequency domain, applied waveform technique. So you are not getting any. So now you can easily detect the transmit signal SK. How? Just simply one tab equalizer. Just divide by GK, YK by GK, you will get the transmit signal. That's it. So that means how nicely you can have a single tab. That is the beauty of waveform, that if you use cyclic prefix, you can easily done by single tab equalizer. You can easily recover the data by single tap equalizer. That's why WebDAM, no one going to leave WebDAM in 5G and 6G. That is the very beauty of WebDAM. Okay. So architecture so nicely it has been designed. So another point of negative point of WebDAM is what? If we'll go towards highly time varying channel, what will happen? If you go towards the highly time varying channel, so what will happen? This circulant matrix, if you write use CP and remove CP, after that you see that this will be no more circulant. That is the negative point. This WebDAM is providing better reliability only frequency selective slow fading channel. But if you have a fast fading channel, what happens? This will be no more circulant. So what will happen if it is no more circulant? Here some interference will come, that is known as inter symbol you can tell, but in practical you can tell inter carrier interference. Since you are doing transmission in carrier frequency in frequency domain, its name is inter carrier interference. So inter carrier interference will come here. That means, are you getting? That means if you are using frequency selective fast fading, you will get inter carrier frequency, inter carrier interference for WebDAM. So now the question will come, how I can mitigate this one? Then in 2018, from that onwards, it has been a new modulation technique is evolved, that is known as OTFS, orthogonal time frequency space. This is being suitable for highly time varying. It is suitable for all. That means slow time varying channel OTFS will be exactly similar to FDM. But highly time varying channel OTFS has the structure of OTFS will be completely different if you go for the highly time varying channel. Okay, that means how what will happen highly time, how OTFS came to, what is the name? Orthogonal time frequency space. What is happening something here? Let us discuss about the OTFS. So before discussing about OTFS, I will just tell you some points to you that how can we represent a channel? Channel can be represented, that means channel impulse response, okay, can be represented in 4 different variants. What is those? Either you represent in time and delay, we have already discussed, or you represent in time and frequency, or you represent a delayed Doppler, or you represent in Doppler and frequency. Out of which, how to get time delay? If you have, you know, the Fourier transform, you will get time frequency. Here to here Fourier transform along the time, along the time, you will get delay Doppler. Getting my point? So like that. So here time delay and time frequency. Time frequency we are using in OFDM. Okay. Its Fourier is SFFT. It is known as symplectic finite Fourier transform. Its Fourier, you will get delayed Doppler. Okay. Its inverse, if you will do inverse symplectic finite Fourier transform, you will get time frequency. So that means these are the 4. Basically, we will consider delay Doppler and time frequency. Okay. Now we have considered till now time frequency and delay time. Okay. In multi-carrier WebDAM, we are using the channel as time frequency representation. But what we have seen that with the time varying, there is a lot of channels. Channel will vary with respect to time. Its frequency response also varies. Now let us see what will happen to the channel if I'll consider the channel response. If we represent the channel response as a delay Doppler. So you can observe here some diagram. I'll just show first, then we'll go back here. Yes. This is one scenario. Okay, this have been taken from one research paper. Okay, this one scenario, you can see that you have a transmitter. Better you will understand here. Yeah. So this is some transmitter you have. So transmitter, this is one receiver. So you can see how many paths you have. 1, 2, 3 paths. Okay. So accordingly here you have some paths. It is a transmitter. One path. This is a receiver. One path. Another path. Another path. Okay. All this receiver. So 3 paths you have. So 3 to 4, some more paths, maybe whatever path, 4 paths you have. So you can see that 4 paths you have here. You represent this channel response in time frequency. What you see, each time you have, and at each time and each frequency, you have some channel taps. At each time and in frequency, you have some channel taps. What you observe, same thing in delayed Doppler domain. Here, see. Here, almost every time, every frequency, you have channel taps. Here you can see what? You have only 4 number of channel taps at some delay and some Doppler. Why it happens? Because each channel tap, each path is associated with a delay and a Doppler. That's why whenever you represent the same channel in time frequency or in delay Doppler, you'll see that two different variations you'll see. You'll observe two different variations. So here also same thing. So what idea you got here? So if you want to recover the channel in time frequency domain, you have to estimate all channel taps. See how many channel taps are here. Here, if you want to recover the channel in delay Doppler domain, you have to estimate only 4 channel taps. So that is the advantages of representing channel in delay Doppler. Now here I will tell another one very interesting thing. What is happening here? You can observe that one transmitter transmits some signal, you have a receiver. So this path, this color you can see it has some delay almost zero because it's a line of sight path. And Doppler, it is moving little bit speed, so you have some Doppler. Okay, Doppler I have written in index form. Okay, that is actually I'll tell you what is this index later on. So this that means you just understand that now this is some Doppler is here. Okay, you can see this yellow paths. Yellow path is what is happening. This is on the receiver, so it is this vehicle is moving little bit faster than this receiver. So that's why it has more Doppler. Okay, and so it is little bit farther from here. That's why delay is little bit more. That's why it is in this grid. Understood this purple one. This one, what is happening? This vehicle is moving towards. That means in opposite to this is moving in this direction. This is opposite. That's why Doppler is negative here. Okay, and it is getting reflected from here. That's why it has a delay which is more than other two. That's why it has more delay. And you can see the width, the radius of the circle denotes what channel gain it has. How much distance, more distance, so it has less channel gain. So that has a less radius. Okay, so these are something. Now you can observe that same experiment has been done after some microsecond. What you see that? You see the two different channel. Here channel, same location, this is there. But little bit modification happens only last one. Because this vehicle came now. So now what you observe? So channel is not highly time varying if you consider represent the channel in delay Doppler domain. If you represent the channel in delay Doppler domain, you will observe that channel is not highly time varying. So that is a noble thing it came that is known as coherence time. That is a geometric coherence time. Geometric coherence time depends on the environment reflected elements, reflected parameters, which is not changing at high rate. That means you cannot see that it is changing very high like coherence time. So there is a geometric coherence time is little bit larger, greater than the coherence time. That's why delay Doppler channel, you can tell the delay Doppler channel is approximately constant for a time varying channel. Okay, so that is the reason why we are going for the delay Doppler representation. Now let us come to the OTFS. So OTFS basically follows this system model. What you have to do here? You have to transmit the signal in delay Doppler domain. Take the constellation symbols in a matrix form. Transmit signal at kth Doppler and lth delay. Convert this delay Doppler to time frequency. This conversion will happen. See, we have to convert delay Doppler to direct time. Otherwise, you cannot transmit. But this conversion, direct conversion is known as inverse Jack transformation. If we do that, we cannot use OFDM. That means we cannot use OFDM concept with OTFS. That means what? If I have a OFDM chip, we cannot implement OTFS using OFDM. That's why one thing is what we can do is we will follow two-step transformation to get delay Doppler to time domain. How we'll do that? First, we'll do delay Doppler to time frequency. That will be done using ISFFT, inverse symplectic finite Fourier transform. Then we'll do Heisenberg transform. Heisenberg transform, what it will do? It will convert time frequency to time. Okay. Then you transmit through channel. You have received signal. Then you do the reverse operation. Time domain to time frequency you convert. That is Wigner transform. Then time frequency to delayed Doppler you convert. That is by SFFT. This is inverse to ISFFT. Okay. Like FFT, IFFT, you know. So this is ISFFT and it is SFFT. Your received signal will be in the delayed Doppler domain. So now there will be challenge how I can mention, how I can develop a system model that with the relationship between yk, l and xk, l. Okay. So that is the key point now. So what you have to do is, so this you understand what is the time frequency and delay Doppler. How I told you na, these are the symbols you keep in the Doppler, time frequency. So you just see the pictorially what is happening. If the time frequency, time is a delay Doppler, convert two-dimensional ISFFT through two-dimensional ISFFT, you can get time frequency. That means if you have n number of symbols in time and m number of symbols in the frequency domain, that you will get corresponding here m number of symbols in the delay domain and n number of symbols in Doppler domain. So you have to transmit in delay Doppler, you will make it ISFFT, it will spread, this symbol will spread along the time frequency. So finally, so what is, you can observe that here delay Doppler grid, this is the time frequency grid, this is the delay Doppler grid. M delta F 1 by NT is the resolution of Doppler. 1 by M delta F is the resolution in the delay. Okay. This is the, that means the resolution factor in delay and Doppler. So that means here you can understand the how a delay Doppler symbol can be converted to time frequency. That means in time it will take the delay Doppler. If you have n number of Doppler bins and m number of delay bins, so that means you will get a symbol having m delta f. M delta f is the total bandwidth and nt is the total time duration of the OTFS symbols. Okay. So next is how we can do one by one processing. We have first ISFFT, right? This is the ISFFT operation. Then we have Heisenberg transform. This is Heisenberg operation. Okay. So once you have ISFFT operation, through Heisenberg, how you can do Heisenberg? You have to use the transmitted pulse. Then you will get a S of t, the time domain signal, continuous signal. Then you transmit it. Then you have a receive signal. Then you do the Wigner transform. Then once you Wigner transform, you do, here you will get what? Here you will get y n comma m, which is equal to summation over n prime 0 to m n minus 1 and m prime 0 to m minus 1. This is h n comma m x n comma m plus noise. Okay, this y n comma m, what you have had, this complete summation, all these things, this is nothing but the relationship between receive signal in time frequency domain and transmit signal in the time frequency domain, and this is the channel in time frequency domain. This is the relationship in time frequency domain. That means what this relationship is, that means this relationship is nothing but here to here, YNM with XNM. But we have to do so you can do, see, you can develop relationship between here to here, you can develop also relationship between here to here. So you have to see that which relationship will give you the better to design a data detection and efficient data detection and channel estimation techniques. That's why I told always designing the system model is plays a critical role to get all other means all other necessary design of necessary things like channel estimation, data detection, all these things. Okay, so here one point, okay, this expression. So now what happens that here time frequency representation of the channel, this one time frequency representation of the channel, yes. So then SFFT. Okay, now you have to do the SFFT operation. SFFT are the receiver. Okay, SFFT converts time frequency to delayed Doppler. So what I already told these things. Okay, now what will happen that you can represent this signal. This signal you can represent in vector form. How you can do that? Here one concept is there. One concept is here. So what pulse you are using? This will give a cross ambiguity function. If you will use, so you can observe that the present signal will have an interference with other time frequency signals. Okay, that you can have completely nullify it. If you assume a what the pulse, that pulse is a like localized, so that is localized over time frequency. You cannot have a pulse which is localized both time and frequency, but we can have a pulse which is localized in delay. Approximated, we can have a pulse which is localized over delay Doppler. That's why we can get in delay Doppler domain less interference. That's why you have a this expression. So some things you have to study from the paper. So but finally I wrote this is some I think uh, some equation has been cited but forgotten to cite. Okay, so this equation you can just see equation 23. What is the equation 23? This equation 23 is the you have to transmit signal X is in delayed Doppler domain, receive signal Y in the delayed Doppler domain, and H is the channel matrix. So this equation actually you will get when you will get how you will get that complete description. You have to see some paper, but I can tell you that from where you will get this thing. Once you do this operation and then you apply the mathematics concept, then finally you will obtain a matrix vector product. Here you will very interesting thing you will get. One is using ideal pulse, one is using practical pulse. So here I am explaining only using ideal pulse in this slide, in this presentation. If you use ideal pulse shaping, what will happen? This channel matrix will be become a block circulant matrix. What is the block circulant matrix? You can see here. Yeah, this is a block circulant. Along with it is sparse. Sparse means what? There are many zeros. As I told you that delayed Doppler have less number of channel taps. That means there are sparse in nature. That's why this channel follows a sparse block circulant. Sparse block circulant means this block circulant. Why it is block circulant? Because all these matrices are circulant at this. See, A0, A1, A2, A3 you have. A3 is coming here. A0 is here. A1 is here. A2 is here. Then A2 is coming here. A3 here. A0 here. A1 here. A1 coming here. A2 here. A3 here. Then A0 here. So this is known as sparse block circulant structure. The A0 is this thing. So this is some example. I have taken one channel. You can see this is the channel impulse response in delayed Doppler. Channel impulse response in delayed Doppler. So here you can see that you have how many channel taps? Only two channel taps. What is first one? H0. So it has a delay tau minus 0, delay and Doppler. It has delay 0 and Doppler 0. That's why this is the representation of the channel in the delay Doppler domain. You can see that K naught K1. This is the index correspond to delay and Doppler. Here you can observe. Here what you have? You have a delay. Delay is tau minus 1 by this thing. So it has a delay of 1. That's why delay index. L1 is delay index, that is 1. And Doppler is also 1. So this is the index. So that index actually how you can get actually that is some
Hello, sir. Sir, you are not audible. Sir, I think you are muted from your side or you are not audible. Or there is a network issue. let's wait for a few seconds. I am trying to communicate Dr. Himanshu sir to continue the session.
Okay, so let me share again. Okay, sorry for this interruption. So I think we have ended with this some highlighted research work of our group. So it is visible, right? Okay. So here, Pradeep, that is visible, na? I think.
It is visible.
Okay. So some highlighted research of our group. So we have developed a low complexity linear data detection for MIMO OTFS system. So you can follow our papers. Theoretical bit error rate derivation we have done for OTFS systems, and also OTFS we have derived the sparse channel estimation technique, and in the context of RIS. So RIS is a novel technology that some one of you are doing, that is nothing but known as the reflecting surface, intelligent reflecting surface, that will be used to program the channel. So you can smartly you can program the channel using RIS. So also in the context of RIS OTFS, this work we have done. So this work you can follow here. What we have designed, that design of reflection coefficient for low complexity zero forcing equalizer. Here we have used, you have designed the low reflection coefficient, have considered low complexity zero forcing equalizer, and you obtained that the zero forcing equalizer. We have derived zero forcing equalizer along with designed the reflection coefficient, which will provide the minimum bit error rate. Okay. Here also in context of hardware implementation, we have done some work on FPGA, so MCOTFS and Jack OTFS. This is some work we have done in FPGA. This work also we have done on FPGA. Okay, so basically these are some references you can see about OTFS, MIMO and all. So thank you for this presentation. If you have any doubt, you can ask me, you can have a discussion.
Okay, everyone, participants can ask any questions. Please go on. Any participants wants to ask any question, please go on. Okay, sir. Actually, I have two questions.
Yes.
About sir Heisenberg transform and Wagner transform. Can you?
Yeah. Let me just. I have just. Yes. So you have Wigner transform and.
Yes, sir.
Yeah. What is your doubt? What is your
Sir,
question?
can you elaborate it little bit?
Wigner and Heisenberg.
Yes, sir. Yes, sir.
Okay. So what will happen, that you transmit the constellation symbols in delayed upload domain. Okay. Transmit the constellation symbols delayed upload domain. Then what you have to do? You have to transmit. You have to convert this delayed upload signal to time domain. So how you can convert that? Here we are using the two-step method. If we use a direct step method, what will happen? This part will not be there. The wave dim, I will explain. Let me explain. So if you do the two-step method, what will happen? That delayed Doppler to time frequency, you are converting ISFFT using ISFFT. then time frequency domain to time using Heisenberg. What is Heisenberg? If you see that this is nothing but the FFT operation. Sorry, IFFT operation. So that is the converting time frequency to the time. That means each time one frequency, you see that Heisenberg is nothing but IFFT operation. And the receiver, what will happen? Time domain to time frequency. That is Wigner is nothing but FFT operations. Okay, that's why these complete things will come as OFDM. That means you can see that OTFS as a OFDM, it has some prior pre and post processing. One is ISFFT, one is SFFT. Understood? So this is the something. Heisenberg means what? It's converting time frequency to time. Wigner is converting the time to time frequency. It is just opposite Wigner and Heisenberg. Then this complete framework is for the OTFS. Am I clear? This thing.
It is clear.
If you want to go through, that means you have to go to all the complete mathematics equation. This is ISFFT. This is Heisenberg. Then you have to write the receive signal. Then Wigner transform. Then you will get all these expressions. This is the relationship between time frequency. That means this is the relationship between this and this. See, YNM and XNM, you will get one relationship. You can have the relationship YKL and XKL. YNM XNM relationship is this one. Whereas YKL XKL relationship is, I have not written in symbol form, but I have written in vector form, the 23. This is a relationship YKL and XKL. These are some beautiful expression because H is follows a block circulant structure, so you can easily exploit that structure to detect the data. Okay, am I clear?
Yes, sir.
If anything else,
If anybody want to ask a question to sir, you're free to ask. Please go on. Please, Ajitha, SS, please go on. Any anybody? Any queries? Please. Okay, sir. I think all have anybody. They have no queries.
okay, ठीक है.
Sir, sir. Um, so, thank you, sir, for your informative session. And sir, all there is lots of mathematics behind it. I think that's why uh, of hesitating to ask some questions. So, but thank you, sir, for your very informative session and
Okay,
encouraging session. And sir, we have a small memento for you for your speech. Please, sir, accept it. And this is
thank
for
you.
you. And we'll send you your mail ID.
Okay, thank you.
Thank you, sir. Thank you for your session. And thank you all.
Okay, thank you. Okay.
Thank you, sir.